Okay, and first, absolute value inequalities, something that you've had before. I'm not sure how much we covered them in there, but you need to refresh yourself on absolute value inequalities. We don't deal with them the same way, right? A less than is not dealt with the same way as a greater than. I mean, if you remember, the first step is make sure that the absolute value is isolated. And in both of these examples, they are. For the absolute value less than, what's the next line when you break it down so there's no more absolute value symbols? What does that look like? No. It is not two inequalities. Okay, an absolute value less than is a three-part inequality. -2, let's see, look at this. -2 is less than x minus 5 is less than 2. Now, if you break that into two different inequalities, then it's a compound inequality, and they got to be tied together with the word and you got to make sure to somehow indicate that. All right. Now, when you see, how do you break down an absolute value greater than? That's when you need two inequalities, right? For an absolute value greater than, you have to say that the x plus 3 is greater than or equal to 7, or the x plus 3 is less than or equal to -7. That is not the way you should be dealing with the less than. Unfortunately, some of you may have been taught that along the way by people that didn't really understand. I guarantee you, anywhere you've ever been taught this, if you looked in your book, that's the way they did it, right? Now, if you break it into two, again, saying that x minus 5 is in between -2 and 2 is like saying x minus 5 is less than 2 and x minus 5 is greater than -2. I mean, that is true. If you're totally careful, I wouldn't mark off for it if you did that. But I would just say, this is really the way you deal with a three-part inequality. And then how do you solve the three-part inequality? Go ahead. Well, you isolate the variable in the middle part, right? In this case, add 5. Add 5. So you got to do 3 times. And now we've got 3 is less than x is less than 7. Now, for these, you got to solve them twice, right? Subtract 3. Or x is less than or equal to -10. Right? The graph of the one on the left, right, has a 3 on the left, a 7 on the right. It's closed circle on both, open circle on both because it's not or equal to, and it's shaded in the middle. It's shaded in between 3 on the left, 7 on the right. Right. This is -10 on the left, 4 on the right, closed circle because it is or equal to, and then the shading, x greater than or equal to 4, that's telling you that the shading is to the right of 4, over here, and that's telling you that it's to the left of -10. And it's tied together with the word or because there's no way that one value could be both less than -10 and greater than 4. Right? So that wouldn't make sense. There is a way that if you did this as two different inequalities, they have x less than 7 and x greater than 3, then you would shade where they overlap. Okay, so brush up on that. Okay, remember what we call these things here? What is it called? No, it's not a system. It's a piecewise function, right? The function is defined differently for different parts of the domain. So the question specifically is, how do you evaluate a piecewise function, right? How do you find f of -1 in this first problem? which one do you plug it into? Right. You look at the domain, right? This one is good for x less than 0. Since -1 is less than 0, use 2x plus 1. Right. And what about when f of 0? Which one? Yeah, I mean, the greater than or equal to 0, the or equal to 0 is on the second one, so use the second one. So just remember how to evaluate a piecewise defined function. Right? These problems on the study guide, again, they're the best that we've got. There's like two parts to the directions. One says evaluate, all these numbers. But really what I'm trying to get at here is it also says find the domain and the range. So for example, on this problem right here, what does the range look like? Is it all real numbers? No. Y is less than or equal to, okay, next come, 1. So again, y less than or equal to 1 is that, the way they write the pre-cal test, because I didn't write this test, I'm sure they'll use the interval notation and say something like -infinity, comma, 1, square bracket, right? That's less than or equal to 1. And the domain is all real numbers. I mean, it doesn't give us the equation, but you could assume it's a parabola, and parabolas are all real numbers. Okay, and then this one, the domain is, I mean, the only point, there is a point of discontinuity here, right? Because I got to pick up the pen and go down here. But if you notice, they're careful to define, it is defined at x equals 1. It's defined there, and then it's open circle there, and it continues on. So domain is all real numbers. What is the range? Yeah, it's greater than -2, and because that's an open circle, it is greater. Not greater than or equal to, greater. So the range is y greater than -2. I'm trying to remember what this one is. Find vertex, x and y intercepts. In a problem like, I think actually this is about x and y intercepts. How do you find, if you're just given a standard function, how do you find the y-intercept? Plug in x equals 0, right? So the first one, the y-intercept is 12. If there's a constant term, that's it, right? So some of these you could tell, y-intercept is 7, 4, -1. Okay, if it's like this, I mean, you would have to like substitute x equals 0 and then solve, -8 squared, 64. Right? Substitute x equals 0, then that's 2 squared is 4 times -1/4 is -1 minus 2, -3. How do you find the x-intercepts or the zeros? Yeah, plug in a 0, let's say this one here, 0 equals 12 minus x squared. So x squared equals 12, x equals plus or minus the square root of 12. I mean, ultimately, if you had to find zeros, what other ways do you have to find zeros? Graphing, right? You put it in the calculator, look for it across the x-axis. If I set something like this equal to 0, it could be that once I FOIL and combine like terms, it could be factorable, something like that. This one is kind of I generally don't assign these, but it's a test question. So we understand what a composition of functions is, right? It's f of g of x is like when you put the g of x inside of the f of x. This one is trying to say, come up with a g and a f of x that would have as a composition this result, right? Let's say, I'll do this one here, the h of x, since it's on the bottom. What if I said f of g of x equals x plus 2, and f of x equals 1 over x? Then what would f of g of x be? 1 over x plus 2, which is this. They're asking you to do that. And when you do this as like a homework problem, they got to say, well, there could be different answers. You may come up with another funny way to do that. But as a multiple choice test question, it's like which one of these could be, then you'll be able to pick out which one it is. What would we have come up with, for example, on, let's do 50. What do you think the inner function would be? No, that's the whole thing. What's the inner function? How about 9 minus x? What if the g of x was 9 minus x and the f of x was the square root of x? Now, when you put the g of x into the f of x, you've got that function. Okay, find an inverse. Remember the steps for finding an inverse? Well, let's take this one, for example. And I'll say that these problems in the book, they say, determine whether the function has an inverse. That's not part of the problem on the test. It just says find the inverse, so you can assume it has an inverse. Remember, to see whether a function has an inverse, that's the one-to-one test. You got to see, does it pass a vertical line test and a horizontal line test? If it does, then you say, yeah, it has one. For example, x to the fourth looks like that. It does not pass a horizontal line test. 1 over x squared looks like that. That doesn't pass. But a linear function, it passes. So assuming that you've got a function which has an inverse, how do you find the inverse? Change the f of x to a y, switch the x and the y, and then solve for the y. Right? That's how you find an inverse. 3y equals x minus 5. Y equals x minus 5 over 3. And that you could say is f to the minus 1 of x. Find an inverse. Right. Given a vertex and a point on a parabola, how do we find the equation for the parabola? Plug it into what? I mean, that's the thing. You're going to have to know the standard form for a quadratic or parabola, right? That is y equals a times x minus h squared plus k. So yeah, you have to plug into that. Okay, what do I plug in? Let's say I'm doing the second one. Well, first, we have to fill in for a, h, and k. Ultimately, there will be an x and y in the equation, right? So the a, h, and k, which can I plug in right away? Yeah, plug in those two right away. Y equals a times x minus 4 squared minus 1. And then you've got a point, so put that point into the x and y, and you'll be able to solve for the a. So it's a two-step. In the end, once we do that, let's do 2, 3. 3 equals a times 2 minus 4 squared minus 1. 3 equals negative 2 squared is 4, so that's 4a minus 1. Add 1, 4 equals 4a. A equals 1. And then substitute that back in there, and you're done. And these are problems that there was more to this in the book. They gave you these and said, list the possible rational zeros, and then there was a graph beneath it to say, and then verify that they do look like the zeros are in that list. How do you generate that list of possible rational zeros? No. The factors of the last term divided by the factors of the first term. So in this first one, the factors of negative 2 would be plus or minus 1, plus or minus 2. And then the factors of the first Well, it's only one. So in the end, these are going to be the possible rational zeros. It doesn't mean that every one is a zero. It means if there is a rational zero, it's in that list. You know, this one might be a little more interesting just because there are factors. There's more factors to go off of, right? It's still -2 at the end, which is plus or minus 1, plus or minus 2. But now you're dividing by the factors of 4, which are 1, 2, and 4, right? So now you got to do that. So now you're not done. Now you got to take all the combinations of what's in the numerator divided by what's in the denominator. So 1 over 1, 1 over 2, 1 over 4, 2 over 1, 2 over 2, but that's 1, we already have it, and 2 over 4, but that's a half, and we already have it. So this is a list of possible rational zeros. So remember how to make that list. Yeah.
Where do you get the factors for the numerator?
You have to know them. What are the factors of -2? What are the factors of 4? It's just basic math.
Well, no, I mean, I didn't know what numbers you had.
2 and 4. Yeah, sorry. Okay. How do you turn zeros into polynomials? Well, how do you turn zeros into factors? For example, if 2 is a 0, what's the factor? X minus 2, right? So now, where this gets a little trickier is, what happens when you have 1 0, which is given, and it's imaginary? Right? If I have a 0 of 5i, what's the other 0? It's got to be the conjugate, right? So there has to be a -5i. And actually, even in a list like, let's say this one here, 1 plus the square root of 3i, you'd have to have 1 minus the square root of 3i. And even if it didn't have an I in there, radical, irrational zeros also occur in conjugate pairs. Because where do they come from? Quadratic formula. And quadratic formula's got plus or minus in front of it. So then, let's say we did this one, right? Just because it's the simplest one to show. If these are the zeros I'm starting with, then I have to say x minus 1 times x minus 5i times x minus -5i. And you're going to probably multiply these two together first, and then take that and multiply it times that. Okay, find the zeros. I think there's a lot that we have to understand about the zeros of a polynomial function. First, looking at this list, how do you know how many complex zeros there are? Complex meaning could be real, could be imaginary. Because altogether, when you add up the real and the imaginary, you get the complex numbers. How do you know how many complex zeros there are? Whatever the highest power is, right? So that number right there is telling you the total. How could you find how many real zeros there are? Calculate, look at the graph. Look at the graph, right? For the most part, you could look at the graph. So the number of complex is the degree. The number of real from the graph, right? X-intercepts. And the number of imaginary what did we say about imaginary zeros? There was one thing that we had to keep in mind. We just did it on the last slide. They occur in pairs, right? So it's an even number. So it's an even number, and you know you got to know that the number of reals and the number of imaginaries are adding up to the number of complex. And what about if you looked at the graph? Let's say you looked at the x to the 5th, right down there, and you saw something like this. How many real zeros do you see? Well, if you say 2, and there's total of 5, how many imaginary is it? But imaginaries are even numbers. How could that be? Because what do we know about the number of zeros when actually the graph touches the x-axis and goes back in the same direction? That means it's there twice. So this is actually 3 real zeros. 1, 2, 3. And that leaves 2 imaginary. Right? So when it goes through the graph, it's there once or an odd number of times. When it touches the graph, the x-axis goes back the same direction, it's there an even number of times, usually 2. But remember, these two add up to this. Right? How do you tell what the vertical asymptotes are? Like on this first one right here, where would we find a vertical asymptote? Rita? What'd you say? Yeah.
Oh, isn't it the power of the?
No. Yeah.
Whatever makes it equal to 0.
Whatever makes the denominator equal 0, right? That's undefined, so you'll have a vertical asymptote on the graph. So what is that number here? It's -2, right? So you would say that this thing has a vertical asymptote, BA, x equals -2. But if you notice in the study guide, it says B and C. Actually, that should have said A and C. Then what would be the domain? If the vertical asymptote is x equals -2, what would be the domain? No. Domain x does not equal -2. Right? If there was a vertical asymptote there, then x can't equal that. And then do you remember what were the rules for finding horizontal asymptotes? Now is where it comes into the powers.
The power of the. I don't know if it was the denominator of it.
Remember, what was the vertical asymptote when the denominator had a higher degree than the numerator? 0. Right? So in this case, you've got an asymptote of y equals 0. Right? What was the rule when they actually have the same degree? The ratio of the coefficients of the highest degree term. So 2/1, y equals 2. And one that's not shown there is, what is it when the numerator is a higher degree than the denominator? There is none. Okay. Remember the compound interest formulas. You'll be given the formulas, right? So the two, I had them up for last block, but you'll be given those. You need to know how to plug in, right? A equals P times 1 plus R over N to the NT. What does the R represent? The annual interest rate, right? So, for example, if it says R is 2%, what do you put in the equation? 0.02, it's a decimal. What does the N represent? T is the number of years. Go ahead. How many times what? That you compound. The number of compoundings per year. Right? So if it says quarterly, that means 4 compoundings per year. If it says monthly, that's 12. 365 daily. Okay. Now, if you have continuous compounding, then you don't have an N anymore. You're taking the limit of this thing as the N approaches infinity. So it's not a countable number anymore. And actually, this thing converges to this formula. Then use that. So there's no more N in it. Right? And the E is the base of the natural logarithm, 2.71828, etc. Right? How do you convert from a logarithm to an exponential to a logarithm? This 5 to the third equals 125. What is the base of the logarithm? 5. Right? What does the logarithm equal? 3. And what goes inside the logarithm? 125. So the bases are the same. The logarithm equals the exponent because logarithms are exponents. Okay, properties of logarithms. Right, we had some properties later, which were like product property, quotient property, power property, but this is more of the basic. How can you simplify when the base of the logarithm equals the base of the exponential, then the whole thing equals the power. It's just 7. Right. How about log base pi of pi? Right. Well, what's the power? It's 1. So the answer is 1. The log base 3.2 of 1. What is the log of 1? Remember, it has an x-intercept of 1. So the log of 1 equals 0. Doesn't matter what the base is, 0. That's a property. And this thing is like the flipping. This is like f of f minus 1. This is f minus 1 of f. Right? 9 to the log base 9 of 15 is 15. Okay, change of base formulas. There is a question on the test which I told them to take off, and they didn't take off. But it said use change of base formula to find this. All right. Well, how would the change of base formula work here? Log base 3 of 7 would be log 7 over log 3. Where now you're using log base 10. But the thing is, that's in your calculator. You have a log base function in the calculator, so you really don't need to do a change of base anymore. And in a multiple choice test, I mean, if you use the log base, that's fine. Get an answer. Right? These are simple exponential and logarithm equations. Usually a simple exponential is what they would call a one-to-one property, where you try to make it the exponentials on both sides have the same base. So this 4 to the x on one side, how could I write 16 so that it has the same base? It's 4 squared, right? So if 4x equals 4 squared, then x equals 2. But you probably didn't need to do that to figure that out. Solve for x. Convert it to an exponential. What would be the base of the exponential? E to the negative 1 equals x. Okay. Now, there will be some more complicated logarithms, but not too complicated. I tried to, the reason I only put 2 problems in here is because I wanted them to be more like the test question. It's not like you've got logs on both sides, but you have more than one log on one side. So how do you put these together? For example, this first one, how do you combine those 2 logarithms into one logarithm? It's called condensing. That would be ln of, because it's a minus, no, x over x plus 1 equals 2. Right, so you condense them into one, convert to an exponential. E squared equals this, and solve. What property would you use here? Yeah, then it would be ln of x times x plus 1 equals 1. E to the first equals this. Yeah, you will eventually. This one only has one problem in it because I wanted to be, make it as close as I could. I mean, note this is an exponential function in a word problem. And what's different about this one, which all their other examples in this section, which is 3, 5, they all start with a constant there. something like KT, and you have to take a step to find the K, and then you've got to answer the question. The question on the test, the constant's there. You've got a number. So I don't remember if it says evaluate. Like this one on the first step says, well, you plug in for these 4 years and you calculate a P. Then it asks, according to the model, when will the population reach 350,000? So it's giving you a number to plug in there, and then you solve for that, right? That's like the test question. Most of the other examples, there's like a two-step. There's a second constant that you got to solve for first. That's not like the test question. So that's the kind of thing you need to know how to do. Remember that if it's something that has years in it, they've probably done something like this to tell you, don't use 1980 as a value. Use 0, right? Well, if 1980 is 0 and 1990 is 10, 20, 30, that's what you would put in. Okay, matrices. How do we do these kinds of things, with matrices? I mean, number one, put it in the calculator. Do you remember how to put a matrix in the calculator? Okay, so remember that matrices are above the x to the -1 button on the 84s. So second matrix, put it in there. Put all your matrices that you want to deal with there, and then you go back to the main screen. And from there, if you wanted to do, if I wanted to do any of these, A plus B, second matrix, 1 minus, I don't know if it'll let me do this, but matrix 2. Yeah, then just go to the screen and let it do it for you there. Right, so store it under the edit, and then do that. You could do them by hand probably just as easy. It's not a very complicated problem. Now here's the thing about the multiplication. When I started putting these slides together, I wasn't terribly thrilled about the problems that I picked and what followed with them. But remember, matrix multiplication is not just multiply 1 times 2, 2 times -1, 4 times -1, and 2 times 8. Right? You do it like this. You're going across the row and down the column. 1 times 2 plus 2 times -1. Right? And that would give you 0 in that column. It doesn't need to be the case that the matrices have the same order or dimensions, but it does have to be that the number of columns here match the number of rows here. And if that isn't true, then you can't do it. And that's why when it says, if possible, because it may not be possible. So you got to have, let's say these two here. What's the order of this matrix? 2 times 1. What's the order of this matrix? 1 by 4. So can you multiply them? Yeah, because these two match, you can multiply them. What will be the order of the result? 2 by 4, right? 2 by 4. What if I switch the order? What if I did a 4 by 1 times a 2 by 1? Then you wouldn't be able to do it, which tells you what about AB and BA? They're not necessarily the same, right? Because sometimes you can do the multiplication in one order, but you can't do it in the other. So AB does not necessarily equal BA, which means commutative property does not hold for matrix multiplication. Right? And this one here, 2 by 4 times 2 by 2. Can you multiply them? A times B. 2 by 4, 2 by 2. No, these two don't match, so you can't do it. So keep that in mind, right? Those two things. Okay, how do you find the inverse of a matrix? if you put it in the calculator, you could do an inverse, right? If you have a matrix that you can put in the calculator, then you would just put it in and then hit that x to the -1 button and it would do the inverse for you, okay? On the test, that's not possible because they didn't give you numbers in the matrix. They've actually given you some letters in there which can't be put in the calculator. So understand that the basic way for a 2 by 2 only works for a 2 by 2. The way you find the inverse is this. A to the -1 equals 1 over, just a second. If A is A, B, C, D with letters, then A inverse is 1 over AD minus BC times, you switch these two, and you put minus signs in front of those two. Okay. So there are some letters involved, which is going to mean you can't just put it in the calculator. You're going to have to do that part. And we didn't do a lot of that. I'm not going to say much about this other than there's 25 questions that are multiple choice. There's 10 that are free response. There's about 5 or 6 that we won't do because we didn't do that. Just because we just didn't do that stuff. It's stuff we'll get to at the end of the year. And then this problem, which is the last of the free response questions, will be an extra credit. If you want to go ahead and look at it, we could look at it more on Thursday. But it's basically, this is a problem that you could set up a system of equations. It would be a 3 by 3 and then use matrices to solve. You know, I think we know this. How do you determine whether it's arithmetic? We just did it. I think we know how to use A1 and D to find the formula for the nth term and how to use the formula to find any term. I think we know how to use A1 and R to find the nth term of a geometric and how to use the formula to find any term. Evaluate. I mean, there is one just like that. All it says is, you know, NCR, evaluate. And how can you do that? Yeah, where is it in the calculator? Math PRB, right? So you could do it that way. Like I say, we can go over this in more detail next time. And then the last is, there'll be a find a coefficient problem. You know, in a binomial expansion, find a coefficient. So let me leave that back up. And